in single variable calculus, the chain rule came about because we wanted to differentiate a composition of functions. Specifically, if we let h of x be f of g of x, then the derivative of h of x is given by h prime of x, which is f prime of g of x times g prime of x. Now, sometimes we would write that as, say, df dg times dg dx. And we would think about this as taking the derivative of f as a function of g and then multiplying that by the derivative of g as a function of x. Now we would like to apply this idea to multivariable functions. So we'll start with an example. Suppose we have a melting block of ice. So we have a cylindrical block of ice that's melting in the sun so that the height h of t and the radius r of t are functions of time. And we want to find the volume of the ice block as a function of time. So volume here of a cylindrical block is going to be a function of the radius, which is a function of time, and the height, which is a function of time. Now the volume of a cylindrical block is going to be pi times the radius squared times the height. So we have the area of the circular base times the height, giving us that cylindrical volume. So we notice that we can change the volume of a cylindrical ice block by either changing the radius or changing the height. And we're imagining that both the radius and the height are going to change over time because this ice block is melting. So what we're thinking is that we'll have some sort of initial ice block, which is a cylinder. And then over time, we expect that to shrink due to the melting so that the height is smaller and the radius is smaller. And so we want to describe the change in volume. So I would like to use an idea from a previous video, which is the differential. So the differential of V, in this case, we said that the change in V is equal to the derivative of V with respect to R times delta R plus the derivative of V with respect to H times delta H. So here we're recognizing that the change in volume is going to have a piece that is how the volume changes with respect to radius times a little change in radius, plus another piece about how the volume changes with respect to height times a little bit of a change in height. Now I'm going to do a little bit of manipulation here. So what I'm going to do is I'm going to divide delta R by delta T and then multiply again by delta T. And then I'm going to do the same thing with the H's. I'm going to divide delta H by delta T and then multiply again by delta T. Now, I notice that there's a delta T in each of the terms, so I'm going to go ahead and divide by delta T. So then this gives me kind of dV dr delta R over delta T plus dV dH times delta H over delta T. And now, hopefully, you'll see that what we have on the left, delta V divided by delta T, well, that's an approximation of the derivative dV dt. So if we take a limit as delta t goes to 0, then what we get on the left is dv dt. And then we have dv dr, which doesn't change because that doesn't depend on delta t. And then delta r over delta t, if we take the limit of that as delta t goes to 0, well, that's really just dr dt. And then if we take the derivative of v with respect to h, then we're going to multiply that by, again, the limit as delta t goes to 0 of delta h over delta t. That's just dh dt. And so this gives us a way to describe the change in volume with respect to time. dv dt in this case is the partial derivative of v with respect to r times dr dt, plus the partial derivative of v with respect to h times dh dt. And this is an expression of the chain rule. So the differential, delta v, that helped us get an approximation of the derivative. And we used that approximation of the derivative to eventually take a limit as delta t goes to 0 to get us dv dt. But what's on the right-hand side is actually an expression of the chain rule. So let's look at the chain rule. The chain rule says, suppose that f of x, y, z has continuous first order partial derivatives. X is a function of t, y is a function of t, and z is a function of t, and those are all differentiable. Then f is going to be a differentiable function of t, and when I want to calculate df dt, I'm going to do a similar thing as I did with that volume. I'm going to do partial f with respect to x times dx dt plus partial f with respect to y times dy dt, and then finally plus partial f with respect to z times dz dt. And that's an expression for the chain rule where f is a function of, say, 3 variables. And you'll notice that if you look at any one of the terms, here, here, or here, each one of those terms looks like the chain rule for a single variable function. We said, how do you find df dt? Well, you would do df dx times dx dt because x is a function of t. But now we have an expression like that for each of the 3 variables that we're going to add together. But hopefully, when you see this sum of products, you can think about this in vector notation. So in fact, we have df dx, df dy, and df dz sitting there. And that is, in fact, the gradient of f. And we're going to evaluate that at r of t. And then, well, we have dx dt, dy dt, and dz dt. That is the derivative of r of t. And so what we have here is the gradient of f dotted with r prime of t. So we have the gradient vector df dx, df dy, df dz, and that's getting dotted with the derivative of r, x prime of t, y prime of t, z prime of t. So this gives us a compact way to write the chain rule. But in fact, this gives us a chain rule that looks a lot like our single variable chain rule. What did we say at the top of this lecture? We said that h prime of x is f prime of g of x times g prime of x. Well, now we have that the derivative of f with respect to t is the derivative of f, in this case the gradient, which is representing the derivative of f, and instead of times r prime of t, we have dot r prime of t, and that's just to make the dimensions work here. So in fact, this expression using the gradient is the multivariable version of that chain rule that we learned back in single variable calculus. So there are going to be times where the chain rule will be best thought of in components. So using df dx times dx dt, etc. And then there are going to be times where it's going to be better to think of the chain rule in vector notation, that it's the gradient of f evaluated at r of t dotted with r prime of t. This second expression with the gradient, we're going to talk about more in a future video and to give us a little bit more understanding of the significance of the gradient. So for now, most of our computations will be using that first expression of the chain rule. So let's go back to our example with the cylindrical block of ice. So a cylindrical block of ice is melting in the sun, and the height is decreasing at 3 centimeters per minute, and its radius is decreasing at 1 centimeter per minute, specifically at the time when r is 15 centimeters and h is 40 centimeters. So because the radius is changing over time and the height is changing over time, we expect that the height will decrease at different rates depending on what the actual height of the cylindrical block of ice is, and the same thing with the radius, that it'll change at different rates depending on what the radius currently is. So here we've specifically targeted when the radius is 15 centimeters and the height is 40 centimeters. So this is quite large block of ice. We're going to know that the height is decreasing at 3 centimeters per minute and the radius is decreasing at 1 centimeter per minute. Okay, so let's just remind ourselves that the volume in this case is pi times r of t squared times h of t, so that the derivative of the volume using the chain rule is going to be dv dr times dr dt plus dv dh times dh dt. Okay, so notice here that my derivatives of v are partial derivatives. That's because v is a function of several variables, okay? But my derivatives of r, those are straight d's, okay? Those are single variable derivatives. They're not partial derivatives because r and h, those are both functions of one variable. Okay, so what is dv dr? So if I take the derivative of v with respect to r, I'm going to get 2 pi r h. And then that's going to be, both of those are functions of time. That's going to be multiplied by dr dt. Okay, and my derivative of v with respect to h, that's going to be pi r of t squared. Okay, the derivative of h is 1 in that case, times dh dt. Now I'm specifically interested at that specific time, what is dv dt? So dv dt at that specific time is going to be 2 pi. My r is going to be 15 centimeters. And my h is going to be 40 centimeters. And then dr dt, okay, the radius is decreasing at 1 centimeter per minute. So it's going to be minus 1 centimeters per minute. And then h of t is going to be pi times r squared. So that's going to be 15 centimeters squared. And then times dh dt, which is decreasing at a rate of 3 centimeters per minute. So that's minus 3 centimeters per minute. Okay. So we can add up all of these terms, and we would get minus 1875. And then let's look at what the units are. Okay, in this case, the units of this first term, notice it's in centimeters cubed per minute. And here, this term is also in, see, centimeters squared times centimeters, so centimeters cubed per minute. Okay, so both terms have a units of centimeters cubed per minute. Okay, that's volume per minute. That's what we expect for dV dt. So it's minus 1875 pi, and in this case, centimeters cubed per minute. Volume per minute. And that is the rate at which this cylindrical block of ice is melting.